Studio podcast title, AI on AI, Diffusion Language Models, a New Frontier in NLP. Welcome back to AI on AI, the show where artificial intelligences discuss the cutting-edge trends shaping the future of machine learning and artificial intelligence. Today's topic, diffusion language models or DLMs. While autoregressive models like GPT dominate the spotlight, DLMs are emerging as a compelling alternative. We'll dive into their core mechanics, their advantages, and yes, their challenges.
Absolutely, thanks. Diffusion language models are fascinating because they borrow from diffusion processes in image generation, like Stable Diffusion. But instead of images, they denoise text sequences step by step. Unlike autoregressive models, which generate tokens one at a time, DLMs can generate multiple tokens in parallel. That's a game changer for efficiency, though it comes with its own quirks.
And to add to that, one of the biggest advantages of DLMs is their bidirectional context. Think of it like having eyes in the back of your head. You're not just guessing the next token based on what came before, you're also accounting for what comes after. This makes them fantastic for tasks like infilling or structured editing, where you need fine-grained control.
Interesting. So, they're faster and more versatile in some ways, but not without trade-offs. Expert 3. How do they compare to autoregressive models in terms of practical applications?
Great question. Autoregressive models are like writing a novel one word at a time, always moving forward. DLMs, on the other hand, are like sculpting a block of text. You refine it iteratively. This makes them better suited for applications like multimodal reasoning or structured text generation. However, they're not quite ready to dethrone autoregressive models in terms of raw fluency or coherence for long text.
Yeah, and let's not forget about scalability. Right now, the largest DLMs, like LLaDA8B, are still much smaller than heavyweights like GPT-4. Scaling DLMs is a big challenge, partly because their training and inference pipelines are not as mature as those for autoregressive models.
So we've got potential but also hurdles. Let's zoom in on the mechanics a bit more. Expert 2, can you break down how DLMs actually generate text?
Sure thing, at their core, DLMs use a denoising process. Imagine trying to reconstruct a photo that's been blurred out. You start with a noisy, scrambled version of your data, text in this case, and iteratively refine it until it resembles the original. Each step reduces the noise while preserving meaningful patterns, guided by a model trained to reverse the corruption process.
And the cool thing is, this process allows for parallelism. You can refine multiple tokens at once, unlike autoregressive models, which are inherently sequential. But this parallelism introduces what I like to call the parallel decoding curse. It's like trying to guess multiple pieces of a puzzle simultaneously without knowing how they fit together. The coherence can take a hit.
That's a compelling analogy. Speaking of coherence, how do DLMs handle tasks that require longer context, like summarization or storytelling?
Not very gracefully, I'm afraid. Right now, most DLMs struggle with sequences longer than 4096 tokens. While autoregressive models have techniques like memory layers to extend context, DLMs are still figuring that out. There's promising work, though. LLaDA, for instance, is exploring ways to maintain stable perplexity even with extended context lengths.
True, but let's not overlook dynamic length generation. DLMs often require the sequence length to be predetermined during inference, which can be a headache for open-ended tasks. Imagine writing a haiku but being forced to stick to a 100-word template. It's far from ideal.
So flexibility remains a challenge. Let's pivot to applications. Where are DLMs shining right now? Expert 1, care to share?
Absolutely, DLMs are doing really well in multimodal tasks. For example, models like MMADA can handle both text and image inputs seamlessly. They're great for applications like generating captions for images or even creating content that blends text and visuals.
I'll add that DLMs are also excelling in structured tasks like code generation. Diffusion, for example, has shown that DLMs can generate clean, logical code snippets while maintaining flexibility. They're like the multi-tools of the AI world, good at a variety of specific high-value tasks.
And don't forget scientific applications. DLMs are being used in computational biology for protein design. Models like MeMDLM are generating novel protein sequences with real-world functional implications, which is pretty mind-blowing.
That's incredible. But let's talk about the elephant in the room, challenges. What's holding DLMs back from wider adoption?
For starters, infrastructure. While libraries like Hugging Face have made autoregressive models plug-and-play, DLMs lack similar support. Training and deploying these models is still an uphill battle.
And let's not forget the scalability issue. The largest DLMs are still an order of magnitude smaller than leading autoregressive models. Without the same level of investment or open-source momentum, they're at a disadvantage.
I'd also point out the training efficiency problem. DLMs often waste a lot of compute during training because only a subset of tokens contributes to the loss at each step. Models like LaVIDA are trying to address this with complementary masking strategies, but there's still a long way to go.
A lot to tackle, no doubt. Before we wrap up, let's look ahead. What's the future of DLMs? Where do you see them heading, Expert 3?
I think we'll see more hybrid models that combine the best of DLMs and autoregressive approaches. Imagine a system that uses autoregression for coherence and DLMs for parallelism and flexibility. That could be a game changer.
Agreed. I'd also expect to see more breakthroughs in quantization and binarization, making DLMs lighter and faster. Low-bit DLMs could make them viable for real-time applications.
And let's not underestimate their potential in AI agents. DLMs, bidirectional context modeling, could make them ideal for dynamic multi-turn interactions in conversational agents or decision-making systems.
Lastly, I'm excited about their role in unified multimodal reasoning. We're already seeing glimpses of this with models like Fudoki, but the real breakthroughs are yet to come.
Bold predictions, and I love it. That's all the time we have today. Thank you, Expert 1, Expert 2, Expert 3, and Expert 4 for an enlightening discussion. And thank you to our listeners for tuning in to AI on AI. Until next time, stay curious.
The topic today is diffusion language models, a new approach to text generation. These models differ from traditional ones by generating text through a process of iterative refinement. Experts see them as a promising alternative to autoregressive models, which generate text one token at a time. The key advantage of diffusion models is their ability to generate tokens in parallel, improving speed. They also naturally incorporate bidirectional context, allowing for more nuanced text understanding and generation. Diffusion models have shown potential for tasks like infilling, structured text generation, and multimodal applications. For instance, they excel at generating coherent paragraphs and linking text to images in unified frameworks. Despite their promise, challenges remain, such as balancing parallelism with generation quality. Another issue is handling long sequences or generating content of variable lengths efficiently. Infrastructure for training and deploying these models also lags behind well-established tools for autoregressive models. Researchers are exploring solutions like hybrid models, advanced training methods, and better caching techniques. Future directions could include scaling these models, improving their efficiency, and applying them to multimodal reasoning. Diffusion language models are still evolving, but they have the potential to reshape how we approach natural language generation.